So today my talk will be a little bit technical, and I think if you are a database user or database engineer, maybe you will like it. First of all, I want to do a very quick introduction of myself. My name is Ed. I'm the co-founder and CTO of PingCAP, and I consider myself as still a software engineer. I think I'm still coding or reviewing code every day. Yeah, and my interest is in distributed system and database system, and also I also play guitar, and I have my own band. Okay, and I also the big fan of open source, and I think my previous projects like Codis, like TiDB, like TiKV are all open source. So I'm a true believer in the open source and community. So a little bit about PingCAP. PingCAP is the team behind TiDB, and we built TiDB from ground up, just like Databricks and Spark. And okay, so and the PingCAP provides the enterprise level and the cloud-based service for TiDB. I think that maybe some of you have never heard about TiDB before. I would say TiDB is a young project, and but it is widely used in open source community, and a lot of big company are using TiDB in production. And we see that the trend and the community is growing fast and very healthy. Okay, this is some of the users of TiDB, and I think beside this logo here, we think there are more than 1,000 in production users using TiDB every day. I just mentioned that TiDB is a young project, and PingCAP is also a young company. So we started 6 years ago, and now we have it's a PingCAP just 6 years ago. We started from 6 years ago, and I think we did a good job in last past 6 years. Okay. Next, I want to talk about the tech. For you, if you haven't heard about distributed database or database, I want to give the very quick introduction of what is database, what is distributed database. I used to use a metaphor. I always say, hey, database is very simple. It's just like the container of data, right? So let's think about the water is the data. So the bottom, the container of the water is the database software. So and the distributed database is also very easy to using the same metaphor is very easy to understand. So I think there are two methodology to build a distributed database. One is using something like sharding technology to, if you have a lot of water to store, you may have a lot of bottle to keep the water. But maintaining a lot of bottle is very painful, right? So another methodology to build a distributed database is to build a elastic, huge bottom to store water. So it is two kind of the way to build a distributed database. I will talk about uh, these two direction in next few slides and the pros and the cons. Okay, but why distributed database or why TiDB, right? Because we think that the enterprise are you know uh, growing very fast today, and um, but the infrastructure, I think they are facing a lot of challenges in the infrastructure level. Like um, maybe today we just invented too many databases. Like we have time series database, we have graph database, we have Hadoop, we have MongoDB, we have MySQL, we have Redis. A lot of database create the data silos. I think it's very painful to maintain a lot of data stack or technology stack within the enterprise. It's very because yeah, it's very a lot of system is the data synchronization will be a big problem across different data sources. The second, I think nowadays everything is web scale, right? So we have to handle the unpredictable traffic. So that means the uh, the data infrastructure or your application infrastructure should be elastic scaling. That's not very it is a very high standard for a lot of database or systems. Yeah, I just mentioned the maintenance cost. So I think if you are running a big company or you are running the fast growing company's infrastructure, you may be have the same feeling about what I put it here. Okay. Let's focus in database part. The challenge, I think, the under the hood is because one of the root cause, I think, is the separation of OLTP and OLAP. And we have too many databases, but some of them are focusing on OLAP workload, but some of them are uh, OLTP database. But synchronize the data from OLTP part to OLAP part is you have to build a lot of pipelines, like introducing another systems like Kafka, like parser to build the data pipeline across different data source. That is very, I think that's painful, right? And also another big trend is people are moving to cloud, right? So because maintaining the own infrastructure is painful because cloud vendor or cloud service provide a fully managed service for the normal infrastructure. That is good because user experience, right? But from the database part, I think something never changed is the SQL never dies, right? Because if you notice past 10 years, the a big trend is that every infrastructure, data infrastructure, software, more or less they will provide the SQL interface to the user because I think nowadays uh, we have a lot of legacy codes, legacy application are using Oracle, like using MySQL, using Postgres. If you want to migrate to the new infrastructure, new software, new database, if the database doesn't provide SQL interface, that will be really painful. Okay, so the SQL is a must for still a must, I think, especially in the future. Okay, so in the world is my point is right right now everything is web scale. You have to have the scalability in different layer and the different abstract of your infrastructure stack. But nowadays, our infrastructure world is fragmented. So what we can do and what TiDB think about how to fix that. Yeah. Before talking about how we dealing with the situation now, I want to say why now? What has changed? Why not like 20 years ago? Because it is why now? Why 6 years ago we decide to start our own business to 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 fix the problem? Because I think past 10 years the industry we did a great job in made a great progress in creating new hardwares like the network cards like high-speed SSD. So I think past 10 years we made a great change in the hardware industry. So we have the foundation to build a distributed system like the to get a balance between the performance and scalability, right? So for example, nowadays within data center, your bandwidth can the bandwidth is big enough to feel like you access the remote disk just like access the local disk. The throughput is I think the throughput is even higher than your accessing some local disk sometimes, but latency is a little bit higher, but I think it's acceptable nowadays in the modern data center. And also more in the software part, we have a lot of new technology, new algorithm like Paxos, like Raft, that makes us have the foundation to build a high availability, scalable system. And I think also like Spark, like some distributed MPP database like Greenplum brings they have did a great job in creating a distributed computing framework to make SQL. SQL is just like it's a language, but how to combine the distributed system and the SQL together to leverage the computing resource in the cluster to analyze data, right? Using SQL. So a lot of new technology and new algorithm to we can have them to build a modern system. Okay, and of course the cloud. I will not to talk more about the cloud. I will live in the next part. Okay, of course. So today I will talk about some next part. I will talk about some we have the hardware, the software, a lot of new technology to as the background, how we can put them together to build a new system. That what's the frontier of the distributed database design, and what is the challenge nowadays or in the future. So this is my I will talk about this topic in next few slides, like the data distributed strategy, replication strategy for the high availability and data consistency, and transaction, how to get the asset compliance and the transaction support, and the query processing. And I will talk about the challenge we're facing, like how to dealing with the hybrid workload, or how to build a cloud native architecture for database. Okay. First, data distribution. Right. The first big problem or big question for the database designer is how to distribute the data, because you cannot put all the data into one physical node. So right, because we are building a distributed database. So choosing the data distribution strategies is very important. I put it in. I think in general we have two ways to make the data sharing strategy or data distribution strategy. One is static, another is dynamic. I will put it in the example, like if we have a table like this, the user ID, the location, name. The static sharding strategy is really simple. For example, we can choose a column, or we can choose a sharding key, and to split the table into different table by using the sharding key, using some hash function or another. For example, in this case, we are choosing the location as the sharding key. So the Seattle will be placing in one node, the Washington DC. The data with the location of Washington DC in another table, like New York. So this strategy, why we call it static, is just because the before we sharding, we have to choose sharding key, right? But what if the static sharding strategy have the good parts is we can have a strong data correlation, right? For example, if we just want to, our queries just happen in, for example, we have the sharding key, like we want to count star from all the data in Seattle. So all the query, all the workload will happen in this shard, right? So that means this strategy have a strong data correlation, and also it is really easy to implement it, right? So for example, using this strategy, the database is Redis. I think Redis is create some kind of middleware to do that, to choose a sharding key and split redirect the data, split the data according to the sharding key. But on the other side, the bad part of this methodology is like you have to, application have to choose some column. That means the database should have the application logic. That is not very, that means you have to design the sharding strategy. Another big point is data screw, right? For example, if you choose the wrong sharding strategy, like for example, you have tons of data with the location with Seattle, but you have just one or two records with the location in Washington DC, that will make the data screwing, right? And using this methodology, another big problem is that sometimes you have to choose the for example, sometimes this kind of system are like middleware. So it is built on top of the database. So the resharding, the rebalance have to rely on the underlying database. Like that's very complicated to build a very flexible dynamic rebalance. For example, you have for example, if you want to reshard your data using another colon or another sharding key, you have to move the data around, and yeah, it's very complicated. Yeah, because the different uh, the different storage node, they don't have the global picture of the whole database. For example, you cannot do the transaction across different MySQL without the centralized transaction management. So that means you can very yeah, it's really hard to build a strong consistency and a robust data rebalance system using this methodology. But on the other way is using some I call it dynamic sharding strategy. But it is very hard to build a elastic scaling or dynamic data sharding strategy for relational database. I think before PingCAP, before HTAP, before I think before Spanner, I don't think in industry they have we have implemented we have combined the dynamic elastic scaling with the to the relational model. I think relational model is not very friendly to distributed system, right? Because in the age creating relational model, we don't have the distributed system, so the design is yeah is just not very friendly. So, but how to fix that? I want to quote a saying from David Wheeler: "All problems in computer science can be solved by another level of abstraction or indirection." So our in TiDB or I think in today's state-of-the-art distributed relational SQL database, we use the same method or the same methodology. Is we mapping the relation model to the very flat, huge key value form or key value map, right? We are not, because relation model is very complicated, very is not very friendly to the distributed system. But building the distributed key value database is not that hard, right? So our thinking is that why not we make under the hood, we store the data in key value format, but make users consider it is a relational database, right? So we can carefully design the encoding of the key and store the record data into the value part, but and we create a translation layer to make the key value pairs organized to show to present as a relational database. Okay, so that's the problem. That's the strategy we choose. So the problem will be sharding to make the data distribution strategy for the key value database. So the key value database, sharding for the key value database is a solve the problem. A lot of systems have done this before, like HBase, like Sandra, like DynamoDB. So the problem is what's the strategy we choose is, the key design point is we choose range-based sharding or the hash-based, right? The range-based is this hash, like for example, the key to use a hash function to get a result, and using some consistent hash or some model operator to decide which store to keep the record. But the range-based sharding is we create the range and different ranges in charge of the different range of in different nodes. Okay. So in my mind, if you want to build a relational database, I think using the range-based strategy is a good way to choose. Yeah, because in the real world use case for the SQL database, a lot of workload is like select star from the table or the table scan. Table scan is a very normal operator or very normal operation for a SQL database. So choosing the range-based data sharding strategy will have a better performance compared to the hash-based, because hash-based data sharding method is really friendly to some write-heavy or random write-heavy workload, but it will sacrifice the read workload or the table scan performance for a database. So yeah, we have made a trade-off here. Yeah. Okay. Under the hood, building the dynamic sharding strategy is, I think the key is that to create, when we choose the range-based sharding, how to do the dynamic data placement. I think the key is in TiDB, I think the key is to create 4 key primitives or operators. If you carefully implemented this 4 atomic operator, you can have a very robust data scaling or data placement foundation. It's split, merge, clone, destroy, just 4 operator. Yeah, it's not very hard to understand. I will put an example. For example, if you the split and merge is very easy to understand, right? When a range, for example, we have a continuous key value pairs, we call it a range A. For example, the data within the range A is bigger and becoming bigger and bigger, and exceed a threshold like 96 megabytes or 500 megabytes, something like that. We can have a split in the middle of the range to make it 2 different range. And on the back, on the other side, on the other way, when you have some operation like delete range, you can have the merge operator to move 2 continuous neighborhood range back to 1 range. Yeah, this split and merge. And clone and destroy, I will use an example. For example, we want to move the range A to another nodes like this. First, we have to create a new clone of the data of this range, and destroy the old replica in the or the old copy in the original node. So so the result is you can see the data movement. That will define the data movement. Yeah. Okay. This is data sharding strategy. We choose the dynamic and using 4 primitives to create the elastic data movement and dynamic balance. And the second big problem is consistency and high HA. I think in distributed environment, the only way to ensure the data durability is to create more copies of data, right? Because every physical node have the possibility to, anything could happen, right? For example, the crash, the disk is corruption, yeah, the power outage, something like that. So the only way is create multiple copies, but the problem is how to keep the consistency across different copies, right? In the old days, for example, we have MySQL. We are using the older way is the source and replica, the leader and the follower replication. And the MySQL introduced another way to do the replication, call it semi-sync. But I think it is not fixing the very important problem, is because the leader and the follower replication cannot fix the split brain problem. For example, if you want to keep the 2 database with strong consistency, but the only way is that you have every write have to write. You have to get the ACK from both two database. For example, when you have a write, you have to get the or the database flag safely stored data. You can return back to the users. Hey, it's okay. But in this case, you sacrifice the availability. For example, if the network or the synchronization link is crashed, you cannot provide the service on both data center in this case, because when you have to, when you accept write in different data center, you will have the inconsistency snapshot for your data. Okay, this is split brain problem. But in academic world, we have some modern consensus algorithm to make a balance between the consistency and the availability. Like we call it RSM. Okay, the replication state machine. The popular data RSM algorithm is Raft and multiplexers. I think under the hood, they are just the same thing. I just think Raft is a simplified version of multiplexers. So it's basically the same thing. Okay. I will not jump too many details in Raft protocol, but I would say it is it's a modern data replication model with the automatic self-healing ability, or and have a good performance compared to if you want to have a strong consistency. Yeah. Okay, because safe shutdown is really hard. Okay. And but how to keep the, for example, if you build a consensus, for example, like we back to the data sharding here, we split the whole key value map into different ranges. Every range is a data replication group. But the problem is how to keep the data consistency across different range, right? Because, for example, range 2 have nothing to do with the data consistency with range 1, right? Because they are owned by the different replication group. Okay, but the only way to keep the strong consistency across multiple data range or in different nodes is two-phase commit. This is the only way. We don't have another way. I think some people may challenge me. Hey, there is 3-phrase commit algorithm. There is, like 1-phrase commit, something like that. But I think 3-phrase commit is just another way to. It's basically is a 2-phase commit. It's a optimization for 2-phase commit, the trivial 2-phase commit algorithm. So today, the only thing we have in the academia world is 2-phase commit. Yeah, but the 2-phase commit is sacrified consistency. No, not consistency. The performance, the latency is a big problem of 2-phase commit. So the normal way is to build the 2-phase commit on different ISM group, the data replication group. Yeah. So the big challenge I just mentioned, one is the biggest challenge is latency. In past 3 years, I think I spent a lot of time to create a lot of optimizations in our transaction model to make 2-phase commit protocol faster. I think Spanner have a very creative way to use hardware to, like the atomic clock to allocate the timestamp, but we don't have true time. We don't have the atomic clock in the open source community, right? So we have to build a software clock to get the performance, the latency, get the balance of the throughput and the latency. So in TiDB, we choose we create new algorithm in TiDB 5.0. We combine the 2 different algorithms, like percolator. Percolator is also another paper published by Google, introduced 2-phase commit algorithm in the key value data store. And another good paper is a good way is HLC, hybrid logic clock. I think CockroachDB using HLC for their transaction model. In TiDB 5.0, we combine these 2 model together to create a new kind of 2-phase commit. I will to support our local transaction. I will not jump too much details here. If you are interested in this, you can follow our blog. I think I will write something about this in the near future. So I think there are a lot of ways to make trivial 2-phase commit performance better. Yeah, so the result is the performance is acceptable compared to the traditional database. Okay. Well, query processing. a big topic. I think from a very high level, the SQL query processing will be divided into 3 layers: SQL parser, optimizer, executor. But when the SQL processing, SQL database compares to the combining with the distributed system, I think the parser is not the key point. The key point is how to make the SQL optimizer and the executor distributed, right? In the cost function part, we have to introduce some new cost function like network latency cost, data shuffle cost, locality, consider into the optimizer. In the executor part, we have to introduce some distributed operator like the predicate pushdown or aggregation pushdown to leverage the computing power from different nodes. For very simple example in TiDB, for example, if TiDB handle the query like this, we have a predicate here and we have aggregation here. So the computing node of TiDB will push down the operator to the TiDB nodes with the specific data, because we just mentioned that the data is split into different range in different nodes, and every node can have a local data scan and get the partial result and aggregate in the computing node to get the final result. Last year in this year in TiDB 5.0, we introduced a new processing mode. We call it MPP. It's not very hard. It is not very. We just introduced a new operator. We call it data shuffle. So basically, it will create a distributed hash map across different computing nodes. Okay. Last part is I will give a very quick briefing about the challenge and the challenge here.
It's like this sensation in the mouth.
Okay, good. Well, the first challenge is I just mentioned that nowadays the workload is becoming, I think, hybrid. You cannot tell the difference between in some case you cannot tell the difference between is it an OLTP workload or is OLAP workload. For example, sometimes you can just want to run. For example, if your database provide the full feature of SQL, like you can join, you can you can do some very complicated subquery, join, group by, and sometimes you just may want to run some query on your production database, right? But for example, like if you are running an e-commerce application, a website, you just want to see, hey, how much revenue we have made today, some query like this. So the quickest, the simplest way is just to run the SQL query on your transaction node database, right? But nowadays the best practice nowadays before TiDB is to move the data using some technology like the ETL to move the data to another Hadoop cluster or the Snowflake or another data warehouse to run the query on our AP part. But why not we can have a single database to do the transaction and do the analytical on the same database? Yeah, that's our if you have this kind of database, that will be very promising, right? so this is a business. It's a trend. We have a lot of HTAP hybrid workload nowadays, more and more. Another big trend is how to use the cloud native architecture to refactor the database. Yeah, I think Snowflake have a very good start, but I think it's just beginning. I think every infrastructure software will be reshaped by or refactored by the cloud infrastructure. So I will talk about HTAP and the cloud native a little bit. In the old days, just like I mentioned, ETL using a lot of separated data processing software to generate the report or do the ad hoc query. But you cannot just run in the AP query on your OLTP database because that will slow down your TP database. But the challenge is this architecture will bring the complexity for your data infrastructure. And another thing is that the data freshness will be another big challenge, because once you have migrated data to another database, that means it is not the same data. That will lose the MVCC version, the transactional information about your record. So sometimes there will be a big problem especially for some financial applications. So yeah, and nowadays everyone wants to know what's going on right now. Yeah. So how TiDB solved this problem? We just remember we created we split the data into many small ranges, and every data range is a replication group. In our we create a very unique way to solve the HTAP problem is we create the extra copy of every small data range. But the copy is a columnar store. And yeah, so from the user's perspective, our AP, because our storage layer and the computer layer is totally separated. So the computing layer will redirect the AP query, redirect to the columnar store, not to the row store. And the data in the in columnar store, we call it type flash nodes. It is a raft linear. It will not involve into the OLTP part, but it is synchronized the data in real time using the replication data replication mechanism. Okay. So the good point of this architecture is we separated the data replication into many data ranges, right? So it will not have a centralized data synchronization pipeline. It will separate it into many hundreds or thousands or millions of data group, the replication group. Okay, that will be scalable. And we can also leverage the different benefits from the different data format. For example, in columnar store, it is really easy to, really fast to, we can have a good performance for table scan, the operator like table scan. But in the row-based data format, we can have a good performance in, random index lookup. But in this architecture, we can combine these two benefit together. It is something the OLTP system or the separated OLAP system cannot do. The hybrid. So And also because I just mentioned the OLAP workload just only happen in the AP node. So that will be a good way to do the resource isolation. So last year I published a paper about TiDB's HTAP architecture. It said we have experiment here. We can see the OLAP workload will not affect the OLTP performance. But the same experiment happening MemSQL that will cause a big performance downgrade here. Yeah, it's the experiment result. So another challenge is cloud native. I think I just mentioned the cloud infrastructure is reshaping the database infrastructure, right? For example, for example, the Snowflake is building the whole database on top of S3, right? S3 is a service provided by cloud, so that means you cannot, Snowflake is a software that cannot on-prem deploy on your data center because it is totally cloud native, because it's built on top of the S3 API or S3 service. So that's it's a great idea. I think I always said in last 5 years, I think the Snowflake's paper, the Elastic Data Warehouse is the best paper in last 10 years, I think, from my point of view. So I think that the same method will happen in maybe in the future in TiDB or in other cloud native data warehouse, because this is the diagram of the benchmark of S3. You can see the throughput of S3 is very good. Yeah, it is very elastic. Okay. Wrap up. So this is my today. All of the points I want to talk about. So some important topics, important problems lying in the industry, database industry, and in the future, the big problem or big challenge we have to face too. So my vision is in the future, we want to bring the database back to the old day, like 60 years ago. We don't have OLTP and OLAP at that time. Every workload can happen in the same system. So yeah, that will be very simple to the user, very easy to use. Okay, thank you.